Hello everyone. We continue our discussion of current voltage characteristic of a PN junction, and last time we analyzed in details from qualitative point of view what's going on at the PN junction and at the interface, also with depletion regions, when we apply forward bias. So we discussed that we reduce the height of the potential barrier, we increase dramatically density of diffusion current, and drift current remains more or less the same because it was very small. So we have certain quasi-Fermi levels because we push system out of equilibrium condition. And also we get some charge carrier concentration profile for minority charge carriers in respective regions. So our question was, what will be concentration of holes and electrons here at the edges, and also how this concentration of minority charge carriers will change in the adjacent to regions to the edges of depletion regions. So that is important information, and we will now focus on trying to understand this. So let me find where we stopped. Yes. This we can close. Okay, so we are interested now, as was shown on previous image, on concentration NP at minus WP, which is edge of the depletion region in the P-type of semiconductor. And also we need to know minority charge carriers, which are holes. What's going on? Which are holes in N-type region. So that is coordinate WN. So we can give this, define this concentration in terms of the position of quasi-Fermi levels for respective charge carriers, and that will look like follows. NP at minus WP is equal to Ni, intrinsic charge carrier concentration, times exponent EFN minus I EIP. This is position of energy level which corresponds to the middle of the band gap in P-type region, divided by KT, and N, sorry, it's not N, the other one is PN. WN will be equal to Ni times exponent minus EFP minus EIN divided by KT. So here we operate with intrinsic charge carrier concentration. So you need to remember what it is. So we can define it as Ni equal to Nc, effective density of states at the bottom of the conduction band, times exponent minus EC minus EI divided by KT, means when our Fermi energy level is located at the middle of the band gap. That same we can write for from the point of view of holes from valence band. So it will be NV, effective density of states for the top of valence band, times exponent minus EI minus EV divided by KT. So this is intrinsic charge carrier concentration and position of the Fermi energy level in the intrinsic semiconductor will be given as EC minus EV divided by 2 plus KT over 2 natural logarithm ND, that is not, that's about effective density of states NV divided by NC. So that is the way how we determine position of Fermi energy level in intrinsic semiconductor and intrinsic charge carrier concentration itself. So that's as a reminder, we definitely had these equations before. So now let us go further and determine what will be equilibrium charge carrier concentration of minority charge carrier concentration in neutral regions. So that will be NP naught. It is equal to NI times exponent minus EFP minus EIP divided by KT, and PN naught equal to NI exponent minus EFN minus EIN divided by KT. So what does it mean? Let us take a look here again on the our image. So we consider this neutral part. So here it is neutral part in p-type and neutral part in n-type, which are under thermal equilibrium condition. So this is also, this part is also neutral part. But this part is not in thermal equilibrium condition, because you see here we have quasi-Fermi level, which means that we out from equilibrium. And here is also. So we just, with last equations, we determine concentration of minority charge carriers in the neutral region, which is in thermal equilibrium. So that is like this. Concentration is along this axis. So this is our NP naught, the value. So we determine this thermal equilibrium charge carrier concentration of electrons in P region and holes in N region. And first we had equations for these concentrations of non-equilibrium charge carriers at the edges, minus coordinate minus WP and coordinate WN. Okay. So now, taking this into account, let us write the expression for intrinsic charge carrier concentration in from the last like let's consider this equation and express Ni from this equation. So it will be Ni is equal to Np naught times exponent minus EFP minus EIP divided by KT. And then we need to substitute this expression into the expression for non-equilibrium charge carrier concentration of electrons at the edge of the depletion region in the p-type semiconductor. So we substituted like here. So we will get Np at this interface of the depletion region and neutral region in p-type semiconductor. That will be Np naught times exponent minus EFP minus EIP divided by KT times exponent EFN minus EIP divided by KT. So now what we have here, these guys will cancel each other. So this and this. And eventually it will be Np naught times exponent EFN minus EFP divided by KT. So actually what we end up with here, so it's difference between quasi-Fermi energy levels. And difference between quasi-Fermi energy levels, the magnitude, how much they split from each other, shows us how much we are out of equilibrium condition. What is the reason for pushing this system out of equilibrium condition? That is external bias. So it's actually this potential difference which we apply to the terminals of this p-n junction. So that will be Np naught times exponent, and that could be this difference between quasi-Fermi energy levels could be substituted by QV divided by KT. So that is very important expression because it gives us the relationship between equilibrium minority charge carriers in the neutral region of p-type and applied bias to the p-n junction in order to determine concentration of minority charge carriers non-equilibrium at the edge of depletion region, neutral region, where we inject a lot of charge carriers, and that's why there we have more charge carriers than in equilibrium condition. So assuming that V is larger than 0, so we will also consider another option when V is negative, means we have reverse bias. So that will be already a bit different. But now we have this, and this is for minority electrons in P region, but also we can write Pn Wn minority non-equilibrium charge carriers at the edge depletion region, neutral region in the n-type semiconductor. In analogy to the previous, it will be Pn naught times exponent Q times V divided by KT. Oops. And with this, we already know what will be this concentration at the edge. So what is interesting for us and what is important in terms of charge transport, we need to know the concentration of excessive non-equilibrium charge carriers. So we need to take this total concentration, subtract equilibrium charge carrier concentration, and we will get this delta N. So we can write the delta NP, concentration of excessive non-equilibrium charge carriers, which in this case are injected charge carriers, at this W minus WP coordinate will be equal to NP, total concentration at this coordinate, minus NP naught, which is equilibrium charge carrier concentration. And eventually we get NP naught times exponent QV divided by KT and minus 1, because NP at minus WP is equal to NP naught times exponent, and here we just have NP naught, so we take out parentheses this NP naught and we get exponent Q times V divided by KT minus unity. So that is concentration of excessive non-equilibrium charge carriers at this interface. The same we can write for holes in N-type semiconductor at coordinate N, and that will be PNWN minus PN naught. This will be Pn naught out of parentheses, and here will be exponent QV divided by KT minus 1. So now we have these two equations which are important for us. Let us draw some schematic representation of this situation. So we have axis X, then we have depletion region, so it's WP plus WN. This is 0, so this coordinate here is minus WP, this one is WN. And here, let me maybe change color, make it more visible. Here we have our minority electrons, and here we have minority holes. So at these points, right at the interface between depletion region and neutral region, we have concentration of minority charge carriers, which will be equal to NP naught times exponent QV divided by KT. Here it's Pn naught times exponent QV divided by KT. And also in terms of so that should be equal to delta P N plus Pn naught. So this delta Pn, which we determine just there. So it means that we have total concentration of minority charge carriers. And the same here, it will be delta N P plus NP naught. So that is already known, and what is the key here is known in terms of applied bias to the PN junction. So here we have this V. And now the next step, we need to understand what will be this profile here and here for excessive non-equilibrium charge carriers, which are like delta n p and as a function of x, and delta pn as a function of x. So we determine them right at the edges, there's interfaces between depletion and neutral region, but we want to know, so it's kind of boundary condition which we will use. But in order to get the distribution, we again need to write the discontinuity equation, the continuity equation, and it will tell us the exact equation which describes this charge carrier, excessive non-equilibrium charge carrier profile in respective regions. So let us do that. Again, we assume that these charge carriers always remain minority charge carriers. We don't have high levels of injection, means we don't push into these neutral regions too much minority charge carriers that they become comparable to majority charge carriers. That means that we always have diffusion of minority charge carriers in both cases, and as we discussed last time, in this case, within this very short, about 10 to minus 9 second time interval, Maxwell relaxation time, which defines this, their charges are compensated, and this time is much shorter than their recombination lifetime, how long they exist. That means that we will not deal with any space charges in these neutral regions because of diffusion. So we operate again only with diffusion of these excessive minority charge carriers in the PN junction. So another thing, probably before we go to deriving equations for these profiles, we need to consider also reverse bias. So far we were talking about forward bias. Obviously we inject charge carriers, and that's why we have this charge carrier, excessive charge carrier profile, which is high next to the interface and goes down approaching equilibrium charge carriers. But that is true for forward bias. Now let us consider that we apply some reverse bias, which is VR, let's call it like reverse voltage. We consider this as less like than 0, negative sign. Then we can write that EFN minus EFP is smaller, not smaller, it's equal to QVR, and that is negative. So in this case, what happens there? We significantly increase the potential barrier and increase the internal electric field in the PN junction. So if potential barrier increased, means potential barrier, we automatically understand that this is potential barrier for diffusion of majority charge carriers. So then this diffusion current will dramatically, it will further decrease. It was already quite small because of existing potential barrier under equilibrium charge carrier equilibrium condition, and we apply more external electric field in the same direction. It causes increase of potential barrier. So we can maybe show this figure from.
Excuse me, can you
Yes, sure. Oh, no. That's not where we want to go. And this. Okay.
According to this graph, the concentration of where minus Vp is equal to the concentration of Vn, yes? According to this
Yes.
level, they're equal, yes? Or it's different?
You mean that like here and here? Oh, it can be both. It can be either bigger or smaller. It all will depend on the level of doping of N and P type regions. But here we consider that they are more or less the same, because that's the case when we have symmetric p-n junction, so the thickness of the depletion regions are similar, and then the concentration of these excessive like non-equilibrium charge carriers, minority charge carriers in both regions will be the same. But if we have very different doping level, they can be different, and later we will actually show that in asymmetric junction, when we have heavily doped p-type, for instance, and normally doped n-type, only diffusion component of current from low dope semiconductor will make a major contribution. So we can neglect with contribution from extremely doped one. So here's this one. So this is this part left. This is about forward bias. When we have more charges at the interface, this minority charge carriers, than equilibrium charge carriers. They are here, like equilibrium minority charge carriers. That's because we reduce this potential barrier. So that is Q times VBI minus V. And V here is positive, so it actually we subtract. So that's why we increase diffusion of majority charge carriers. But when we have reverse bias, so we increase this potential barrier. It becomes quite huge. So it's the same Q VBI minus V, but now V is negative because it's reverse bias. And what actually happens here? So we increase electric field, which causes and defines drift current of minority charge carriers. Means we extract minority charge carriers from respective regions. We extract electrons from p-type and holes from n-type semiconductor. If we extract them, then the concentration of these minority charge carriers next to the edges of the depletion region, like here, will be smaller than equilibrium. So that is equilibrium charge carrier concentration. So here it's higher. So here it's high, and here is equilibrium. So concentration is high. Here is opposite. Here is equilibrium, but since we extract them from the adjacent regions to neutral regions to depletion regions, we end up with a situation when we have less equilibrium charge carriers than they're supposed to be at given temperature. And then we have also some profile of their distribution deeper in the neutral region when they eventually approach to this equilibrium condition. So let us show it quantitatively. So it comes out from our equations quite clearly. So we know that, let's write it here, Pn at Wn, so let's write it for holes, is equal to Pn naught times exponent minus QV, here we will put R, divided by KT. Oops. And now delta P n at this coordinate Wn will be equal to Pn Wn minus Pn naught equilibrium. But here you see that since we have minus here, it will be, this guy will be much smaller than this guy because this exponent is with negative argument. So means that we subtract from something smaller something bigger, so this delta Pn will be actually smaller than 0. It will be negative. So we will indeed have smaller concentration of charge carriers at the interface we consider than in the neutral equilibrium part of the n-type semiconductor. So that is true for minority holes. We can write the same for minority electrons, and P minus WP is equal to NP naught exponent minus QVR divided by KT, and delta NP will be equal to NP at minus WP minus NP naught, and that is also negative value. So that's why our profile will look like this. So we have our axis X, again our depletion region W, and here we will have smaller concentration. Let's change. Smaller concentration at the interfaces, but once we go deeper in the neutral region, they will, concentration of these minority charge carriers, which are holes in electrons in n-type, in p-type and p, and holes in n-type regions. They will increase and reach somewhere. Here will be equilibrium and P naught, and here will be P and naught. So that is about forward and reverse bias, how polarity of applied external bias changes the distribution of minority non-equilibrium charge carriers close to the interfaces of depletion region and neutral regions. So now, as I mentioned before, we need to determine profiles of delta. Let me change back to more neutral color. Delta NP as a function of X, and delta Pn as a function of X. So in order to do this, we need to set the continuity equation, assuming that we have only diffusion of minority charge carriers. So that will look, we already did that similar stuff because we considered just this case of diffusion of minority charge carriers last time. So it will be d square. Let's do it for holes. Delta Pn x over dx minus delta Pn x over Lp LP square. Can you remind me, please, what is this LP?
Square root of
diffusion coefficient, and what else there?
time.
Recombination lifetime. Yeah. So, and how do we name this parameter? Diffusion length. Yeah, it tells us how far non-equilibrium, like minority charge carriers can diffuse in semiconductor. So that is LP is equal to square root dP times tau P. So we already know that this type of differential equation will have this general solution, delta P n as a function of x should be equal to C1 exponent minus XLP and plus C2 exponent XLP. So that we know from previous discussion. We solve this differential equation step by step. So now this is general solution. We need to solve it with respect to our particular case. So that is, we need to determine this constant C1 and C2. Our boundary conditions, delta Pn at Wn is equal to Pn naught exponent QV divided by KT minus 1. It's like this. And delta Pn at infinity, like very far from the interface, should be equal to 0. So we should not have any excessive non-equilibrium charge carriers, minority. They will go, the total concentration will go to minority charge carrier concentration under equilibrium condition. So now we can substitute this infinity instead of x. So that will be 0 concentration equal to C1 times exponent minus infinity divided by LP plus C2 times exponent infinity divided by LP. So this guy will be equal to 0, and in order to have 0 here, this also should be equal to 0, so that comes with C2 equal to 0. So now we can substitute the first boundary condition, that at coordinate Wn it will be equal to this expression, so it will be P n naught exponent QV divided by KT minus unity. That will be equal from this general solution. We know that C2 is already equal to 0, so it will be just C1 times exponent instead of x we put Wn, so it will be minus Wn divided by LP. And with this we can determine C1. C1 will be equal to Pn naught exponent QV divided by KT minus 1 times exponent Wn divided by LP. So that is our constant C1. So the final solution for our excessive non-equilibrium charge carrier, minority charge carrier distribution profile for holes will look like this: delta P n as a function of x is equal to P n naught times exponent QV divided by KT minus 1 times exponent Wn divided by LP and times exponent minus x divided by LP. So that is actually this guy is our C1 constant, which we determine. So we can rearrange it a bit. So it will be Pn naught times exponent QV divided by KT minus unity, and here will be exponent minus x minus Wn divided by LP. So that is the expression for the profile of excessive non-equilibrium charge carriers, like holes in n-type semiconductor. And now when we have this full information about profile, starting from the maximum point and then how it decreases up to equilibrium minority charge carrier concentration, we know that charge transport is happening via diffusion, so we can actually determine the current which will flow in such condition when we have gradient of charge carrier concentration. We have more in one side and less in another. Obviously there will be some diffusion current. So JP, the density of current density of holes in minority holes in n-type semiconductor because of diffusion, will be equal to minus Q times dP times d, like first derivative over excessive minority charge carrier concentration over position, so it d delta Pn x divided by dx at position Wn. We just need to pick up some position because we need to have a coordinate fixed and determine electric flux, like the flux of this minority charge carriers because of diffusion multiplied by elementary charge, and that will give us the electric current. So now we know this function, like this function. This is given by this equation. So we can, what we need to do, we need to take derivative, first derivative over x of this profile of excessive charge carrier concentration, minority charge carrier concentration in n-type semiconductor of this p-n junction. So that's why it was so important to actually get this distribution as in analytical form. So now we can write that it will be equal to minus, maybe I can write it from already here, so we have it in one line, minus Q times dP times Pn naught times exponent QV divided by KT minus 1 times exponent minus W n minus W n divided by LP. And here will be also, because we were taking derivative, will be minus 1 over LP. So we don't have x because we, instead of x, after taking this derivative, we substitute W and the coordinate of this edge between depletion and neutral region in n-type semiconductor. So this guy will be unity because exponential argument of the exponential function is 0. So that will be Q times dP divided by LP times P n naught times exponent QV divided by KT minus unity. So that is our one of current component, which stands for holes, minority holes. It's the same equation, like similar, we can write for electron component, and total current which will flow through the p-n junction will be a sum of these two currents. So it will be written as J is equal to JP plus JN, that is equal to J naught, so-called saturation current, exponent Q times V divided by KT minus unity. And J naught, saturation current, will be equal to Q times dP times Pn naught divided by LP plus Q dN n P naught divided by Ln. Or we can express these minority charge carriers in another form. It will be Q times dP divided by Ln, and here it will be n I square divided by Nd, concentration of donor centers in so it's P here, donor centers in n-type semiconductor, assuming that all of them are ionized at given temperature. That's important. Plus Q dN divided by Ln, Ni square divided by Na. So that is the expression, so-called Shockley equation, which gives the rectifying current voltage characteristic of a p-n junction. So what it will look like when we apply forward bias, then we will have this part active because exponent will be large, forward bias is positive, so it will exponentially increase. When we apply reverse bias, this will be negative bias here, exponent with negative argument will be much smaller than unity, so it will be just minus J naught at reverse bias. So we can show here. That's how ideal current voltage characteristic. It's normalized by current is normalized by saturation current. Voltage is normalized by KT, so it's like Q times voltage divided by KT. But it tells us clearly shows the difference between forward and reverse branch of current voltage characteristic. Here we have exponential increase, and here it goes to saturation. So this is semi-log scale, so we have kind of voltage axis normal, and for current we have in log scale. So that makes sense, because then we can really compare reverse and forward current branches, because there is like huge difference between them. If we just plot them in normal scale, it will be very difficult to see current in reverse direction. So now we need also to show that in case of, let's keep it here, so in case we have P plus N junction, then we have very high concentration of Na, so it's very much higher than Nd. And in this case, we can write so Na here in the denominator. So this term will be negligibly small in comparison to this one. So we can write that J naught can be expressed only by first term. It will be Q times d P Lp n I square divided by Nd. Now we also can highlight how J naught will depend on temperature, how the saturation current will depend on temperature. So we remember that Ni is proportional to exponent minus Eg divided by Kt. Oops. So that's why when we consider temperature dependence, so there will be some T in, let's say, power gamma. It will combine from diffusion coefficient dependence, from NC, effective density of states dependence. There will be some power there, times exponent minus Eg divided by Kt. So I don't specify this number, exactly this argument, but in any way it doesn't matter, because here we have the dominant function, this exponential function. So that will define the temperature dependence of J naught, saturation current of which actually is the reverse current of PN junction. So it will exponentially increase with temperature. That's why if we want to have the maximum possible rectification, means the ratio between reverse current and forward current at the same magnitude bias, let's say 1 volt, minus 1 volt and plus 1 volt. And we want to keep it at a lower temperature, because with lower temperature we will exponentially reduce this reverse current, which is J naught. Now let us talk about reality and ideal world. So far it was ideal world, and now we show here. You see this dashed lines. So this is JV, the current voltage characteristic of an ideal PN junction. However, in reality we have different conditions. First of all, if you take a look at this region, that is so-called leakage current. Leakage current because we have some shunt resistance, so equivalent circuit of a PN junction for DC we consider it for AC. For DC it looks like diode, so which stands for rectifying features of this PN junction. Then we have shunt resistor and series resistor. So here are our terminals where we apply some bias. So this current at low voltage, so at low voltage potential barrier should be quite high, diffusion of majority charge carrier should be low, and we should not observe such high current as here. But because of current flowing through this shunt resistor, we indeed see this, and that is negative factor, obviously, because it adds up current which flows in forward and reverse direction through the. If it matters for forward direction only at a very low bias, then for reverse current it actually matters because it's supposed to be very small. So we will always have some contribution from this shunt diode, which will result in increased current through the device. Then we come, you see this narrow range where actually real current voltage characteristic overlaps with ideal, and this is region of diffusion current, like pure diffusion current. However, there are other mechanisms of charge transport, and for instance, when we have diffusion current, we also may experience some recombination processes or generation processes in the depletion region. So we assumed, as you remember last time, we discussed certain points which should be conditions which should be accepted. We said that there is no generation recombination process in the depletion region. That's not always true. If we have some deep energy level, we may have recombination in this depletion region, and that causes increase, like some additional current transport mechanism for charge carriers at forward bias, and this exponential dependence will be already modified. So for that purpose we have some semi-empirical equation for current voltage characteristic of PN junction. So we can write that current is equal to I naught, which already may be voltage dependent, and in case of generation recombination processes it is voltage dependent. It's proportional, reverse current is proportional to the width of the depletion region, because the wider the depletion region, the more contribution of generation current can be observed and measured, times exponent QV. Here we need to take into account voltage drop over series resistance divided by KT, but instead of, in addition we have here N, which stands for ideality coefficient minus unity, and we close this. So this ideality coefficient tells us how much current voltage characteristic deviates from ideal current voltage characteristic when we have only diffusion current which flows over this potential barrier. And as you see here, we get some deviation in this current voltage characteristic, which tells us that this n is actually not unity, so it can change. For most cases is less than 2 and more or equal to unity. So it changes from 1 to 2. Then we have regions when we inject a lot of charge carriers, and we also have quite significant voltage drop over series resistance. So that is shown here in this voltage current voltage characteristic. In order to get a real current voltage characteristic, we need to take into account this fact, because not all voltage, so here we have axis with its normalized voltage, so not all external bias which we apply to diode, this voltage, is dropping over this PN junction, because it will split. Part will drop here, delta Vs, like Rs, and part will drop here. It will be delta V, let's say diode. So this fact should be taken into account, because every device possesses some series resistance. It is small, and the smaller it is, the closer we will be to ideal current voltage characteristic, but it never equals to 0, and this factor should be taken into account. So this is pretty much everything what I wanted to tell you about current voltage characteristic of PN junction. Obviously, those who are interested in more details would be interesting to learn from quantitative point of view about generation recombination currents, for instance, how indeed they depend on voltage and which other parameters matters there. However, at this stage you know how to derive equation for ideal PN junction, assuming only diffusion processes. And from the qualitative point of view, you can explain that, okay, it can also deviate from this ideal current voltage characteristic, mostly because of generation recombination processes in depletion region, and that's why we deal with like kind of semi-empirical Shockley equation, which is this one, and takes into account voltage dependence of the saturation current, and also effect of parasitic effect of series resistance. So the purpose of PN junction as a diode is to rectify current, and it works really great. It's small size. You can make it in chips, in microprocessors. Introduce these junctions actually everywhere. However, there is one. It consumes very little amount of energy for operation, so it's really great. But it has this J naught. Whatever, if it's even close to ideal, it's still there. So there is some reverse current which flows through the PN junction at reverse bias. Means that this creates certain level of noise, and we can reduce it, but then we need to cool it down, which is an intentional cooling. It costs a lot of money, so where it has to be done, you can do, but still, even at lower temperatures, there is some electric current flowing through this PN junction. So that should be taken into account, and for instance, for you to know that even nowadays, in this time of processors and microcontrollers, the most expensive amplifier, like noise, like sound amplifiers, which have to provide as clear sound as possible at high level of amplification. This professional equipment. They still use these diode tubes with some glass tube with vacuum inside and filament which injects electrons in this vacuum and 2 electrodes in order to get the rectification. Because there, if you don't have electrons, if you don't inject them in vacuum, you don't have electrons, and actually your current is equal to 0. Reverse current. Forward current can be controlled. Here, with all plenty of advantages of solid-state p-n junction, we still get this very small but important, and always we need to try to reduce it as much as possible, reverse current. By the way, we have shown here that reverse current J naught is proportional, let's consider this case of heavily like asymmetric p-n junction, to Ni. So we also highlighted the temperature dependence, but here is also Eg, band gap dependence. So the wider band gap material we use, the smaller will be this reverse current. So it's another factor which could be taken and should be obviously taken into account, because larger band gap allows us to, at the same temperature when we don't cool down, deal with much lower intrinsic charge carrier concentration, and that gives us much smaller saturation current and means current at reverse bias. So these factors need to be understood, and please remember about them. This, let's say, temperature and materials features which determine current voltage characteristic of p-n junction. And so far we considered everything what is critically important about formation of p-n junction. It's capacitance voltage characteristics, and current voltage characteristics. So we considered AC and DC current voltage characteristics and electrical properties of p-n junction. So now this was done until now in the dark, and our next step will be bring some light to studio and check what will happen when we eliminate such a p-n junction and utilize it in this photovoltaic mode. There are 2 options to utilize it in photodiode mode, which we will hopefully have time to discuss a little bit later after we consider first solar cell operation. But solar cells, these are p-n junctions which are operating in photovoltaic mode, and that will be the topic of our discussion for next time. Thank you for your attention. If you have questions, you're welcome.